Today we're going to finish up our counting exercises, Combinatorics, and we've got up here, we just looked at the end of class last time, we looked at the definition of the binomial coefficient. And so n choose r is defined to be n factorial divided by r factorial times n minus r factorial. All right? So let's do an example. So before we talk about R permutations, now let's define what an R combination is. An R combination of elements of a set is an unordered selection of R elements. Is an unordered selection of R elements of a set. Well, what's another word for that? If you have a set and you have an unordered collection of R elements selected from that set, what do you have? A subset. Right. i.e., it is a subset. In other words, it is a subset. So when we're asking questions about how, what's the number of, when we're calculating the R combination, what we're really calculating is the number of subsets that you can have. So let's do an example. Because with subsets, order does not matter, right? Okay, so let's give an example. DAE, the set DAE is a three combination from A, B, C, D, E, F, G. So now the question then is, how many ways can we take a subset of three elements? In how many ways can we take a subset of three elements from this set? So how many three combinations from a set of 7? So here's our question. How many three combinations are there from a set of 7? Well, is it 7 factorial over 4 factorial, or is it 7 factorial over 3 factorial?
7 times 6 times 5.
Or is it something else?
No, that's not.
You don't think so?
No.
Okay, so look. If this were, what if instead of doing an R, what if instead of doing a 3 combination, suppose we were doing a 3 permutation? Suppose we ask, so how many this DAE, if we were doing, if these were ordered, we would have DAE, ordered triple DAE, DEA, ADE, and AED. So these are the 2 start with D, 2 start with A, and then the 2 that start with E are EDA and EAD, right? Okay. So, but the thing of it is, if we were calculating the 3 permutations, how many 3 permutations are there? I mean, we had the 3 permutation before, right?
Yeah, that would be.
Yeah. Right. Yes.
This one they're allowed to duplicate, but it just won't.
No. They're not allowed to duplicate, but the order doesn't matter.
Oh, right.
Are you with me?
Yeah.
They're not allowed to duplicate, but the order doesn't matter. So my question is, if the order did matter, how many 3 permutations would there be? There'd be 7 factorial divided by what? 4 factorial. But now that order doesn't matter, The problem is, all of these are really correspond to just this. So we have overcounted by how much?
6.
Yes. Okay. So all of these correspond to, you know, D, the set DAE. Okay. So P73 is too big by a factor of what?
6.
Yes. So P73 is too big by a factor of 6, right? In other words, but 6 is the same as what? Where do we get the 6? 3 factorial, yeah, 6. Or 3 factorial. So what do we have to do with P73? So what's the answer? So the answer must be what?
Isn't it 6 for every combination we choose, though?
Yes, and that's why it's by a factor. That's why we don't just subtract it. That's why we divide it. You see what I'm saying?
P73 over 3 factorial.
Yes. So it's P73 over 3 factorial. But wait a minute. But what is P73?
That's the same.
The whole thing. That's
7 divided by.
That's 7 factorial. This P73 is
Divided by 7 minus 3 factorial.
Over 3 factorial, 4 factorial.
yeah over 3 factorial, 4 yeah.
That's the whole thing, yeah.
Or 3 factorial, 4 factorial, right? So take a look at 16(9). So 16(9) is what it is in general.
7 choose 3.
It's 7, yeah, so this is 7 choose 3. All right? Okay. And so 16.9 is the generalization. Is everybody clear? And then 1610 is this example that we did, illustrated, the number of R combinations of n elements. So here we defined what an R combination was. And what we just demonstrated here is that the number of R combinations of n elements is n choose R. All right, well, let's do one last exercise. Let's do exercise 16.45. Now, what is exercise? Now, this is a little tricky. It's going to use choose, but let's see if you can.
It's like we have 2.
Well, let's see. Sam and Tim on a faculty of 10. Right? So you've got
10 different
here you got 10 different people. So you have like A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, H, I, J. So here's the 10 people, right? And let's say that
A and B.
A and B can be.
A and B is Sam and Tim. So this is Sam. This is Tim.
Well, we have to have 2 committees, one with Sam.
Okay,
and
and they refuse. They refuse to be on the same committee. See, what we want to do is we want to form one committee of 5 people. Now, obviously, when you form a committee, it doesn't matter what order. It's not like you're the president, you're the vice president, you're the secretary, you're the sergeant at arms. It's not. So the committee order doesn't matter. So we're in this situation, right?
Team A, Team B.
Well, so what we need are, so let's list a few of them. A few of them we could have like A, we could have the set A, D, F, H, I. That's one. Now, do Sam and I guess we don't have to. I guess Sam and Tim don't have to be on the committee, right?
How many 5-person?
No, I guess not, huh?
So another possibility is C, D, F, H, I.
No. Oh, they don't have to be on it at all?
I guess. Well, that's what I'm asking. How do we interpret this question?
Or are they asking us to?
Because I don't think it doesn't say at least one of them has to be on the committee, right? Otherwise, I think, are we interpreting this statement correctly?
When I first read it, I thought it wanted us to come up with 2 committees of 5.
And Sam and Tim will be on the opposite ones every time.
No. It just says one.
5 person.
It says how many 5-person
Yeah, that
committees
makes sense.
can be. I think this is the interpretation. And then another possibility is B dfhi, fhi. But what we cannot allow is the following: AB fhi. So AB fhi. So let's X this one out, right? So what we're saying is that this one's not allowed because they're on the same. So how are we going to?
This is weird.
Yeah, which is going to require some thinking.
Because it's different cases, whether one of them's in it or none of them are in.
Yeah, so it's not. Yeah, it's. That's right. How are we going to do this? Ooh,
Is there addition?
I hear some silence. The silence is deafening.
I was wondering if you could do, well, like 3 different cases. One would be that that Sam and Tim won't be on either of the teams. So you'd start out with a factorial, 8 choose 5. And then we'd have that added to
Oh, that's
what
that.
happens when only one of them does. Which would be,
Well, then we could have one where the one is on it, and then one where the other one is on it. I think we could do that. Actually, I think that would work. I'm thinking of a way that where you don't have to do 3 cases, where you only have to do 2 cases. But I think it's equivalent. I think.
No one's on it or someone's on it.
No, I think that's what he's saying. What I was thinking was, if we could count how many of these, what we could do is we could do the total, just with no restrictions, right? And then figure out how many of these
we'd have to take out.
we would have to take out, and then we could just subtract.
Wouldn't it just be?
I like Ben's way.
Wouldn't it just be 8 factorial you'd have to take out?
No.
8 times 7 is 6. 8
Eight,
choose.
eight,
8 permutation, 8 5.
eight. Well, but these are combinations, right?
Okay, so 8,
So
8 choose 3.
yeah. So here, let's do it your way too, and see if we get the same number.
Okay.
I hadn't.
I'm gonna actually try.
Okay, so here let's do so exercise. So here let's do total. Here's the first strategy. Total possible minus number that contain both. Number that contain both. Okay, so now what would be the total possible with no restrictions at all? It would be what?
10 choose 5.
Yes, that would be 10 choose 5 would be the total minus. Now how many contain both? Well, basically if we require both of these to be in here, then the question is how many would it would be what choose what? In other words, how many
We're only choosing, it's 3 choose, or 8 choose 3. If both
or 3 choose
then there's only 8
eight.
people left and only 3 slots left.
Yes, it's 8 choose 3. Okay. So here it's 8 choose 3, and the way we get this term is it's the other 3 are chosen from a set of 8. All right. So does anybody's calculator have a choose function? Does yours? Does anybody have a calculator that has the choose on it?
Use it.
Well, try well now that we were doing it, get your calculator out and do the choose, and let's see.
8, 9.
Oh, good luck then.
No, yeah, I mean, because after all, here we are. Here you got your calculator, and whoa, you did that in your head? 252 minus. Now, how about 8 choose 3?
I think it's 56.
Jeez. And 252 minus 56 is
96.
196.
Wait.
Is that what you got? Holy moly, that's great. That's great thinking. Okay, so alternate. Okay, so let's do Ben's way. Alternately. Now, so what was the number? So what is it that we're doing?
A choose 5 plus A choose 4 plus A choose
I mean, what's the idea? It's what is adding. What are we adding?
We're
Adding-
adding the case when neither Sam or Tim are on the team,
Neither. Okay, so number with neither
which is there's 8 members.
plus, that's plus what?
Number with Tim and number with Sam.
Plus number with Tim
Plus number with Sam.
plus number with Sam. Oh, okay, and then this number is what?
8 choose 5.
So this is 8 choose 5
And then with Tim is 8 choose 4.
plus 8 choose 4
And Sam's also 8 choose
is 8 choose 4.
4. They're all added.
Okay, and then this 8 choose 5 is what?
8 times, it's 40, or 56.
56,
70 and 70.
140.
An addition sign in there. Up above you.
Oh, plus. And this turns out to be 196 also. We have confirmed. Yeah, that was good. Oh, did you figure out how to do the choose now? Yeah, cool. Okay, so now you know how to use a new function on your calculator, and now you know what it means, and you can. Next time somebody walks up to you on the sidewalk and says, "Hey, Kyle, you know I've got to form a committee," and you can just whip out that calculator and say, "Oh, it's 196." All right, good deal.
Most popular guy.
Okay, let's move on now to the last chapter. Well, not the last chapter in the book, but let me get my eraser here. But the last chapter topic that we will be studying
Let's
this.
go to the infinity chapter.
Yeah, it would be nice to go to the infinity chapter. I'll let you read that on your own.
Summer.
Yeah, good summertime reading. It is. It's quite interesting, and I think now that you're used to doing all of this, proving theorems and stuff, it's a really interesting chapter, and I encourage you. I wish we had time to do it, but if there was one chapter that I would recommend, that would be that one.
Any chapters you want to take out, so throw that one in.
No, I really think all of the other material we did was really useful for computer science. Actually, see, infinities don't really apply to computer science because all computers are finite. All computers have finite amounts of memory. They have finite, even though you're in the gigabytes or the terabytes, half a terabyte of my hard drive, solid state. That's a lot, but it's still finite. And even, 100 years from now, the computers still have finite amount of memory. So infinities don't concern us too much in computer science. All right, so now, chapter 19, a theory of graphs. First of all, let's take a look at 19.1, which is the definition of a graph. Okay? Now, we have actually used graphs previously when we talked about relations. And, but now we're going to formally, that we just use them to draw, to represent things, to visualize. But now we're going to actually define mathematically what a graph is. Let V be a finite, non-empty set. Okay, capital V is a finite, non-empty set. And E, a binary relation. Ho-ho. Now, what is a relation? Hello? What's a relation? It's a set of ordered pairs. So that's and let V be a set of ordered pairs. Then G equals the ordered pair V, which is a set, and E, which is a set of ordered pairs. So does everybody understand? We have an ordered pair, and the first element of the ordered pair is a set, and the second element of the ordered pair is yet another set of, but then that's a set of what? Ordered pairs. So we have all these ordered pairs in an ordered pair, in a set which is in an ordered pair. Are you with me? Just to think about that. And that's called a directed graph or digraph. An element of V is called a vertex, and an element of E is called an edge. Okay, so here's what let's do. 19.1. Let's see why these are called vertices and edges. So this is a 19.1 example. So here is an example of a directed graph, a digraph. What we're going to do is we're going to do this. We're going to let V be the set A, B, C, D, E. And we're going to let E be the relation BB, BC, BD, BB, BC, BD, CE, EC, CE, EC. Oh yeah, nice. I'm glad that you are instinctively classifying whether this is, yeah, what kind of a relation this is. All right. So now, can you? Okay. So now I don't want to rewrite all this stuff. But if we said G equals, then it would be this set, blah 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 blah, right? Comma, and then what would it be? Wait, V is a set. And then the set of ordered pairs, so this would be another set, and then inside this there would be, you know, blah, 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 blah. I mean, here, there would be.
We need to, what is
Well, here, our G would be set A, blah, 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 and then our V would be the set BB, comma, blah, 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 blah. I mean, you see, I mean, if we were to write this, I don't want to write it out.
Okay, so inside G is V and
Yeah, yeah. I just wanted to show you the structure, okay? Okay, but now look, you guys, how do you draw what? Here in math, when somebody, you know, when you were doing algebra and somebody said, graph this function, what was a graph? It was an x-axis and a y-axis, and you know, you'd have a parabola or something like that, right? Okay, unfortunately in mathematics, there's two different meanings for the word graph. This graph has nothing to do with this kind of graph, okay? And a picture of a graph when you're graphing a function has an x-axis and a y-axis, but this kind of a graph looks like this. Yeah, actually it looks kind of like an airline route, you know, or a subway something.
That's the Cartesian plane down there.
Yeah, this is x-axis and y-axis, and these are ordered pairs, you know, that. But this kind of graph it's complete. The meaning of the word is completely different from this kind of graph. And the way we visualize this is we have like here, each one of these is what is this called? V. Each one of these is called a what? A vertex. So the vertex is indicated by a point or a circle. Okay, so here's B, here is C, here's D, here's E, and here is A, right? So these are the the plural of vertex is vertices, okay? So these are the vertices, and then the way you represent it on the plane is if there's an edge from B to B, so this E are the set of edges. So this E from B to B is like this. There's an edge from B to B, and it's directed.
Like
it's from B to B. It's like finite state machines, actually. Yeah, and then from B to C, you know, that's from here to here. From B to D, that's from here to here. Okay. From C to E, so that's from here to here. And then from E to C, that's from here to here. So this is a picture of that graph. All right? Poor A. Yeah, so this graph is not what we call connected. Okay, it's not. If it were connected, you could, well, you kind of intuitively see why this isn't connected because there's no edges, you know, from A to the rest of them. All right. So now in 9.1.1 we have, I've listed out here the definitions from our book, but they're not numbered like this. So I collected them all in this 9.1.1 definition. So let's go through these definitions and see what they mean. So we don't prove any of this stuff now. We're just defining things. All right, first of all, in an undirected graph, VE, E is a set of unordered pairs.
Well, that doesn't make any sense.
It doesn't make any sense. All right, so let me give you an example. 9.1.1 example, 19.1.1. So here's, it would be like this. Suppose we have A, B, C, D. So suppose this is A, B, C, D, and the graph could be drawn maybe something like this. Okay, so this is an example of an undirected graph. Now, what's the difference between what's the difference in the picture? The difference between this picture of an undirected graph and this picture of a digraph, which is a directed graph. What's the difference?
One has direction.
What has direction? The vertices or the edges?
The edges.
Yeah. In a directed graph, the edges have direction. That's why it's called a directed graph. There's an arrow on one. Yeah, in other words, the edge from C to E is different from the edge from E to C. But here, there is just an edge between B and D. It's not, it doesn't go one way or the other. So the edges are unordered. Are you with me on that? Okay. Now, let me just hasten to add that in computing, whenever you implement these things, these graphs in a program, there is the way, what you would do is you would use ordered pairs, but you would do it like this. So here's a computer representation. Computer, just to show you how it's normally done if you were programming these graphs and processing them in a computer. This is A, B, C, D. Normally what happens is inside a computer, all graphs are digraphs. And so to represent an undirected graph, you would everywhere there's one of these, you would actually store it inside the computer like this. See what I mean? So that's just a practical point. All right. Now let's take a look at the second definition. Multigraph. In a multigraph, VE, E is a bag. Oh no. What do we mean by a bag of undirected edges? What's the difference between a bag?
You can have a repetition.
You can have more than one. Yeah. Okay. So here's an example of a multigraph. Oh, multigraphs are undirected. Okay, because does it say that? Oh yeah, it says undirected. Here's an example of a multigraph. All right. You see what I'm saying? This is an example. And why is it a multigraph? Because there's two edges between here and here. All right. Whereas if it were an undirected graph, because the undirected, it's a set of unordered pairs, then there's only, you can't have duplication.
Could be like 3 or 4 edges, like more.
Yeah, more than 2. Yeah. Here, let's do another one. Yeah, it could be like that.
Because it looked kind of like the computer.
Yeah. Oh, right. Yeah, this is a better example. You're right. Yeah. Look better. Yeah. Is everybody clear? So this is an example of a multigraph. Now, okay. Now let's take a look at the end degree of a vertex of a digraph is a number of edges for which it is an end vertex. Holy moly! What does that mean? The end degree of a vertex of a digraph is the number of edges for which it is an end vertex.
So look at the diagram.
Now let's look at the digraph. Here's our digraph. Let's look at our digraph.
It's pointing to something and nothing points away from it?
And, well, what is the end degree? So,
The end degree of D is 1.
yes, the end degree, good,
The end degree
okay.
of B is 1.
End degree of D is 1.
B is 1, C is 2, E is 1.
in degree of C is 2. Are you with me? And how about out degree? What's the next one? The out degree of a vertex of a digraph. So we're talking about, is everybody clear? The out degree of a vertex D of a digraph is the number of edges for which it is a start vertex. So how about the out degree of D? Correct. Out degree of D is 0, and the out degree of, what's another example? Of B is 3. Oh, good example. Okay, and now what else do we have? The degree of a vertex is the sum of its in degree and out degree. So how about the degree of C? Is it just degree? Is that? Yeah, the degree. The degree of C is 1 plus 2, right? Which is 3. Is everybody clear on that? And what about an edge BB for some vertex B is a self-loop. So what about, oh, son of a gun, it's BB. Okay, so BB is a self-loop. And do we have any other ones there? A digraph with no self-loops is called loop-free. Is this loop-free, yes or no? No. Okay? Oh, and here we have a theorem. Haha, does this make sense? 19.3. The sum of the degrees of the vertices of a digraph or multigraph equals 2 times number of edges. Ooh. Okay, let's... Huh?
Because every edge has an end at the beginning.
Yeah. Yeah. Oh, so you already see why that's a theorem. The sum of the degrees. Okay, so let's verify that for this one. The sum of the degrees. Okay, so let's do the degrees of A, B, C, D, E. So A, B, C, D, E. And here's the degree. So what's the degree? 0, 4, 0, 4, 3, 1, 2. Let's add this up. 4 plus 3 is 7, 8, 9, 10. That's 10. And the total number of edges? 1, 2, 3, 4, 5. Yeah. 5 times 2. It checks. Yep. Are we good? In see, the sum of the degrees of the vertices of it says of a digraph or multigraph. I wonder what about this one? Right. Yeah. Here, yeah. Let's do this. A, B, C, D. So let's do A, B, C, D. So this would be what? 3, 6, 3, 2. Are we good? 3, 2. Let's add them all up. 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7. 7 times 2. Checks. Are we good? Oh, now how about 19.4? In a digraph or multigraph, the number of vertices of odd degree is even. Guess what you're going to do?
Watch you prove it.
No, you're not going to watch me prove it.
We're not
We're going to watch you prove it.
No, you're going to prove it.
We have
And
to
how will you prove it?
explain it to us.
Yeah, what in the world does that mean? Yeah, mathematical induction was right. Good call. Okay. So 19.4. In a digraph or multigraph, the number of vertices of odd degree is even.
So there's an even
Okay.
amount
Okay, so here's a multigraph. Oh shoot, I erased my diagram.
Oh, the odd degree. I
Which
get it.
means A has 3, so it's going to be
Okay, so yeah, so in this, so here's the question is which one of these vertices has odd degree?
A and C.
All right, so here's odd degree A and C.
and that's
So this is odd degree because 3 is odd, right? And this is odd degree, right? Okay, so 2 vertices have odd degree, 2 is even. 2 vertices have odd degree.
prove that by mathematical induction.
Yeah, good question. Here, let me write this out. So two vertices have odd degree, and 2 is even. So it would be impossible if you listed the degrees of all the things, and you counted and you just noted which ones were odd. It would be impossible to have. However many have odd degree is an even number.
It's impossible.
It'd be impossible for there to be an odd number of vertices with odd degree. Now, why is, and you're going to prove this by mathematical induction, but what's the idea?
There's always going to be 2 of them.
Yeah, it has to do with the fact that edges are between two an edge is between 2 vertices, and so. But how do you?
If you try and draw a picture of one that doesn't fit that, you will fail.
You will fail. Yeah, but unfortunately, it's not proof by failure of being able to show a counterexample. We don't have a proof by failure to prove a counterexample. Should have that be a proof technique? Well, I tried to prove it and I couldn't, therefore it's true. I mean, I tried to disprove it and I couldn't, therefore it's true. Actually, that's a good point, because you know what those kind of statements are? In mathematics, there's a term for that. That's called a conjecture. A conjecture is something that mathematicians think is true, but no one's been able to prove that it's true. And there are some famous conjectures in mathematics.
Theories are like that.
In fact, yes, it's like a theory. It's not a theorem yet because you haven't been able to prove it, but you think it's true.
Yeah.
And there's a really, really famous one in computer science. P equals NP. No one's been able to prove. Yeah, but yeah, that's
And what's the end?
non-deterministic polynomial. But anyway, there's the idea is there. The idea that's a
Sort function of n log n. How come A is counted as having 3 degrees?
The degree is 3. 1, 2, 3. Look, 1, 2, 3.
But on a multigraph, isn't it going to and from as well? So each one is leaving and coming back to?
Well, you count the degree. No. That's just the computer representation of it.
Okay.
That's just how I'm just saying that's in a computer. That's how you would do it. But mathematically, it's just 1, 2, 3.
Okay.
Are you with me?
But on a digraph, if there was one leaving and coming back to it, it would be 2.
Yes. Yes. Yeah. The same thing applies to a digraph, where the degree is the sum of the in degree and the out degree. All right. But how are you going to prove that? I mean, that is your homework assignment. That is a homework assignment. How are you going to prove it? What is the base case going? Here's the thing: is it going to be induction on the number of vertices, or is it going to be induction on the number of edges?
I feel like it's on the number of edges.
That's right. What you do is you assume a fixed number of vertices, and it's induction on the number of edges.
Do we have to do it for a digraph and a multigraph?
Now you can just do multigraph.
So there are no edges, which means everything's has an even number.
So your base case is there's no edges.
Which means there's no degrees.
Well, there is a degree. They're just all what?
Right, the degree is 0.
0. So how many have?
Which is even.
So how many? So how, wait a minute, so how many of those vertices have odd degree?
None.
None.
So they
And so and what do you know about 0?
it's even.
0 is an even number.
But how do we get to that base?
Well, no, that is the
That's
base
the base
case.
I mean, how do you get?
You must assume what? Yeah, this writing down the inductive hypothesis, writing down what you must prove and what you must assume as the inductive hypothesis is the tricky part.
Prove n plus 1 edges with n edges
Has the number, you have to write it out, the number of,
It's going to be kind of an informal thing, I guess.
well, it's going to be with words, yeah. This is going to be kind of like the coin problems, you know, where you have to, and then you have to think, okay, so how can I add an edge? To make n, how do I go from n edges to n plus 1 edges?
You draw one.
I know, but what are the different cases for connecting an edge between two vertices?
I don't know. Too difficult of a proof.
No.
Too soon.
No. This is good. This is good. Okay. All right, now let's take a look at 19.14.1. Sorry, 19.4.1 definition. A path. Well, when is this homework due? Thursday? Oh, no, the combinatorics stuff is due Thursday, right? Yeah, let's quit here.
Oh,
How about?
probably. So this isn't due till Monday.
Right. Okay, so we will explore paths next time. See you Thursday.